one branch of physics is kinematics. And kinematics is simply a description. Oh, wait, how do you spell description? This is a bad start. Description, did I spell that right? Description of motion. Okay, now what we want, our goal in kinematics is to come up with a very precise way of describing how objects move through time and space. Right? We're moving through time right now, aren't we? We're just sitting here. Are we moving through space? Are we moving through space right now? Yeah. Well, now we're all at rest, right? We're all sitting in our seats. So with respect to the room and each other, we're not moving. I mean, we're not, changing where we are. But we are on a planet that's spinning around its axis, and we are on a planet that's circling the sun, and that sun circles the center of mass of the galaxy, and that galaxy is in motion with respect to other galaxies. So yes, we are moving through time and space in a cosmic sense. All right. And so what we want to be able to do in physics is describe how things do that. And then later on, we're going to describe why things move the way they do. I think that's when we get into Newton's laws. But we're not ready for that yet. So we're going to talk about kinematics. And now, if I have an object, and let me just use an object that I can put easily under the document camera here. I have a paperclip. And I can make this paperclip move. Look at that. That's exciting, huh? So go home and tell your parents, what'd you learn in physics? Paperclips can move. Now, but this is a little more profound than just a silly little paperclip. This paperclip, if I wanted to move it, I can move it in what we call 3 dimensions of space, right? 3 dimensions? I can move it like this. And I can move it like this. But we have 3 dimensions. It can move up and down like this, right? Towards, all right, down. So like this, and like this. Now, when you go see a 3D movie, right? It's really, it's still a 2D movie. It's a 2-dimensional movie. And that is, everything is projected on a flat screen. And that screen only, has this dimension and this dimension. How do they fool you into thinking that there's a 3rd dimension of depth? Well, they actually shine 2 different pictures on the screen. And using those funky little glasses they give you, one of them gets blocked out from one eye, and the other picture gets blocked out from your other eye. And those 2 pictures fool your brain into thinking that objects have depth. Okay, and that's actually, there's little physics in there. Now, actually, if you there is a branch of physics called string theory that believes that space actually has 11 spatial dimensions, not 3. It's just that 8 of them are so curled up on each other that we don't observe those other spatial dimensions, which is kind of mind-bending stuff, right? But don't worry about that, because 3 dimensions is complicated enough. And we're not even going to do 3 dimensions. We're not even going to do 2 dimensions. Okay, we're going to do 1 dimension. Imagine if you went to see a movie that was in 1D, okay? It would just be a line across the screen. It would be a really boring movie. It would be hard to tell what's happening. So 1-dimensional space. Because what I want to do for right now is I just want to be able to describe the motion of an object moving along a straight line. Pretty boring stuff. Except that once I get beyond this 1-dimensional motion, I'll be able to easily extend it to 2 dimensions and even 3-dimensional space, which is more interesting and more real world, right? But I want to start off with something really simple so that we can all get it and then move on to more complicated ideas. Okay, so now if you wanted to tell somebody where this paperclip is, maybe this is somebody's, this is some kind of special paperclip, And so you were going to send a text message to a friend in another class, and you wanted them to get this paperclip. How would you give them directions on how to get this paperclip? You know, raise your hand and give me an idea. What's the first thing you would text them about how to get to this paperclip? Yes. Tell them where it is. Well, okay. Tell me where it is. Where is this paperclip? Under the document camera in physics class. Okay, that's a very good description. Now, if you sent that to a friend, what are you assuming that they know? Where the physics class is, right? And that they know what a document camera looks like, but they probably do. What if they didn't know where the physics classroom is? So what would you have to do? What would you say? Room 902. So what are you assuming?
They know where this is.
That they can find room 902. They know where to look. Okay. Yes?
In the science building, in California, and Clovis in America.
Excellent. Okay, so what you're doing, so first of all, you need to be in America. And then we're going to narrow it down to California. Then Clovis Unit. Now, the science classroom might confuse people because we have two different science kind of things, right? The Energy Academy building, right? And then you move down there. Now, here's the point. Here's the point that I'm getting at. If you're going to tell somebody where something is, there must be a place in space where you both know, you and the person you're giving directions to, agree you know where to start. You both know where to start. Where are you going to measure this paperclip from? Does that make sense? Okay. And we have a name for that in mathematics. The place where we all agree, we know where it is, so that I can compare where everything else is compared to that agreed upon place. And it's called, yes, I heard somebody say it, it is called the origin. So that's what the origin really is. Now we're going to deal with one-dimensional space. So I'm going to draw a single dimension of space. And we call a single dimension of space, when I draw a line like this, we call it an axis. And in fact, I'm going to call it the x-axis. Okay? And I'm going to use meters here in a second. And so, oh, I didn't want to put it there. Hold on a second. I need a better eraser. All right. I'm going to put the origin right here. Okay. Here's the origin. So, here's my agreed upon place. We all know that everything is going to be, we're going to measure the location of everything with respect to this origin. Okay. Now, let's say I need to say how far from this origin is it? Well, if I put the paperclip right here, okay, how far away is it from the origin? Well, I could get a metric ruler, okay, and I could say, so here's my ruler. So I could say, how far away from it is it? You know, and I'll measure that and say, oh, it's 5 centimeters away from that. So I can go 1, 2, 3, 4, 5, and it's 5 centimeters away. But that's kind of a problem. Let's go ahead and number this. 1, 2, 3, 4, 5, 6. And I'm going to make this in meters instead of centimeters, okay? Because what we're going to be doing is we're going to be measuring these little toy cars, these little buggy cars, in meters, how far away from the origin it is, right? So let's put my paperclip, or actually what I can do, and here's the little cars for those of you watching this online. Here's the little buggy car, toy car that we're going to use in the experiment. And so, so what if I say, okay, let me draw the little buggy car right here. Here it is. Here's my little toy car that we're going to use. It's got a little windshield. It's got a little blinking light. These little wheels. It's got a little seat in there. All right. So that's where it is. 1, 2, 3, 4, 5, 6. Let me put a 7 on there. All right. Now, so where is that buggy car? It's 3 meters from the origin. Okay, we have a name for that, and it's called, the location in space something is, it's called position. Okay, now, in physics, we use very precise vocabulary. It's almost like learning another language. If you learn the language and the vocabulary, and it's not, it's going to make everything a lot easier. Okay, so position, it has a very precise meaning. It is the location. Gosh, what's the matter with my hands today? Location as measured from the origin. Okay, it's always measured from the origin. Okay, so I would say that this buggy car has a position of 3 meters. Okay? Now, it's hard to write out the whole word position. All right? I don't want to say position. I don't want to write out the word position equals 3 meters. Why? Because that takes a long time. So what I'm going to do is I'm going to say x equals 3 meters. So that this is a variable name. I mean, this is a variable, x, the letter x, but it represents something real. And in this case, it represents the position of the object along the x-axis. That's why we use the letter x, because we're along the x-axis. And we're saying, and what this means is, hey, I'm 3 meters away from the origin on the x-axis. Okay? Now, but we want to understand how objects move. Right? Now, later on, the buggy car might be over here. Now, here's what I'm going to do. I don't want to have to redraw the buggy car every time because it takes too much time. So I'm going to use what physicists call the particle model. Now, look, I'm going to study the motion of this buggy car. Do I really care about the blinking lights and the windshield? And no, I don't care about that stuff. That stuff is irrelevant to what I'm trying to understand right now. So why should I draw all that stuff? So I'm going to make it easy. I'm going to draw it as a dot. Now, physicists like to try to sound really highly intelligent. So instead of calling it a dot, we're going to say this is the particle model. And so what we're going to do is we're going to treat this car as if it's a little particle, a infinitely tiny little dot in space. Why? Because this just makes it easier. So wherever I draw a dot, that's the location in space of this little car. So here's the position of the car a little later on. It's right here. And so how far from the origin is that? 1, 2, 3, 4, 5, 6, 7. The car is now 7 meters from the origin. So I'll put x equals 7 meters. Yes? Okay, you with me? But here's a problem. X equals 3 meters, x equals 7 meters. That's kind of confusing. I need to distinguish between this position and this position. Well, here's what I'm going to do. I'm going to say, hey, this was my position at the beginning, and this was my position at the end. So I'm going to use little subscripts that mean the beginning and the end. And you probably learned this in math. You did this in math. This is my position initial, and this is my position final. Do you remember that? Math, your final x and your initial x. Okay? So at the beginning of the time interval that I'm looking at, my car is going to be here, and at the end of my span of time, it'll be over here. Okay? How much did my car change its position? How much did it change? 4 meters, didn't it? Right? It moved 4 meters, didn't it? Now, how did you get 4 meters? Yeah. Well, it was at 7. It started at 3, so it went 1, 2, 3, 4 meters. It's easy. So one way to figure out how much it changed its position is to count. 1, 2, 3, 4. All right, that's one way to do it. Now, so we're going to deal in this class with a change. Am I still on screen here? Yeah, let's move it over a little bit. Change in position. And a change in position, well, we have a symbol in math to represent a change in something. What is that symbol? Little triangle. So it's actually a delta. It's a Greek letter, capital D. Okay, so that's but it just means a change in. That's what we use it to mean. A change in what? Position. Well, what letter are we using for position here? X. And yes, later on we will use Y. And in AP Physics, we use X, Y, and Z. Okay, we go into 3 dimensions in AP Physics. We're going to stick with 2 dimensions in this class. So delta X, what does that mean? A change in position. Now, how did you get that change in position? I mean, we know it's 4 meters. Now, one way to do it is to count. Start here and go 1, 2, 3, 4 meters. Okay, and that works. But you don't want to do that every time. Because what if my initial position was 20 and my final position was 100 meters? Would you want to count from 20 to 100 meters? No, that'd be stupid. I mean, it would take too long. What's the easier way to do it? Subtract. So what you did is you could say, oh, okay, we're going to subtract. We ended up at 7 meters, and we'll subtract where I started, 3 meters, and that will say, oh, my delta X is, well, this is equal to 4 meters. Okay? Well, but in general, like if I didn't tell you where the starting position was or the final position was, if we just wanted to write it in general, I would write it like this. Change in position is equal to the final position minus the initial position. Okay. Now, I'm going to do something that some of you have never seen before. I'm going to change this equal sign right here. Here's an equal sign. Have you ever seen an equal sign with 3 lines instead of 2? Some of your math teachers may have done that. But we do this a lot in physics. This means, this little mathematical symbol here means delta X is equal to X final minus X initial because we say so. This is a definition. Delta X, by definition, is the final position minus the initial position. Okay, that's my definition. So when 2 things are equal, because we are defining them to be equal, I will quite often write it like this. Okay? Now, you can just keep the regular equal sign if you want, but this is now, and this, by the way, is called an operational definition. You've been learning definitions of words all your life, since you were first a baby learning how to talk. Well, but in physics we have, and in science we have what are called operational definitions. That is, something is defined by listing a procedure. Okay, by saying, okay, delta X is defined by, hey, do this. Take your final position and subtract it from your the initial position from it, and you've now got your change in position. Okay, that's the definition. You're defining it by telling, through a set of procedural steps. Okay, that's change in position. Now, I've been saying change in position, change in position, change in position. There's a shorter word that we use to mean change in position, and that is displacement. Okay, displacement. When a physicist says displacement, and you're talking about kinematics, they mean a change in position. Okay, so this is the same as that. So I'm going to say displacement. Now, in other contexts, displacement means something different. Like if I immerse something in water, it displaces or pushes away the water of its volume. And so they use the word displacement. So that's a different meaning. That's a different operational definition. But for this class, in this unit on kinematics, displacement means this right here. Okay? So we've got two operational definitions. We've got the operational definition for position. We've got the operational definition for a change in position or a displacement. Okay, now there's one other idea that you need to learn before we can do the lab today, because we're going to be using these ideas in the lab. And that is, we're going to deal with time. Time. Time is time is just a mind-bending, blow your mind kind of idea when you think about it. Why does time go by? What does time mean? How come we can't go back in time? Why does time always flow forward? Okay. And then in some branches of physics, which some of you may study someday, called special relativity, you realize that if I move away from you really, really, really fast, and I have a big fat watch that you can watch, and you have your own watch, our watches won't tick at the same rate. Time can vary from one observer to another depending on their relative velocities. That's why they call it relativity. And we're not going to study that in this class, but it's just an awesome thing to study. So time is really weird. But we're not going to get into the weirdness of time. We're going to stick in this class with a practical, everyday kind of use of time. And there's two kinds of time that we're going to use in here. And the first one is this. Okay, class, according to our schedule, this class ends at 12:04. So right now this class will end at 12:04 p.m. Now let me ask you this. How long will it be 12:04? What's that? For a minute? For 60 seconds? No, I don't mean like 12:04 and 30 seconds. I mean 12:04. How long is it going to be exactly 12:04? 1 second? No, I don't mean 12:04 and half a second. I mean exactly 12:04. A millisecond? No, I don't mean 12:04 and half of a millisecond. I mean exactly 12:04. You don't know? Yes, that's a good answer.
I don't know.
What I'm talking about here, it's a kind of an abstract idea, but it's an instant in time. And an instant in time has no span of time to it. It's an instant. It's kind of like a point on a number line. Like how wide is a point on a number line? Well, that's the wrong question, because by definition, a point on a number line has no width. Remember in geometry you studied points, and then you studied line segments, okay? So that's kind of like what a point, a time instant. Now we call this a time instant, an instant in time. I will also sometimes call it a clock reading, because today in the lab you're going to be taking clock readings. And you're going to be saying, okay, at 3 seconds, where is our buggy? We're going to take our buggy cars and have them move along a number line, and we're going to measure their position at different instants in time. So someone will say, now, and you'll put a little pencil down, and then you'll measure where that pencil is, and that was the position of the car at that instant in time. And so in our imaginations, we're going to imagine that instant was actually a point in time. So you can think of it as an instant in time, a point in time, or a clock reading. Now, let me ask you this. How much time is left in this class? How much time do we have left? How much time before we all get to go have lunch? Okay, well, what time is it right now? According to my watch, it's 10:39. 10, 39. So what am I going to do? I'm going to subtract these, right? You ever carried from this when it's in hours and minutes? See, I can't subtract 39 minutes from 4 minutes. So what do I have to do? I have to borrow an hour. If I borrow an hour, I'm borrowing how many minutes? 60. So that's going to be 64 minutes. So 64 minus 39 is 5. And then see, that's 5, that's 25. Did I do that right? 64 minus 39 is 25. 25 minutes. Now I only have 11 hours, so we have 1 hour and 25 minutes of class left. Does that make sense? I know, because I've been talking too long. But let's pretend, okay? From the time that I started this, how much time has to go by? Well, that's 1 hour and 25 minutes. Okay? Now, this is what we call an interval of time. Or a time interval. Yeah, let me just call it interval of time is fine. An interval, or time interval. Or a span of time. Okay? Now these things are different. When you talk about time, you can talk about it in terms of an instant in time, like what time is it right now? And by the time you're done saying the sentence, what time is it now? The time instant has changed. You can drive yourself crazy. And then you have an interval of time or a span of time. And those are different things. So I'm going to use the letter T to represent a time instant. And a span of time, a time interval, is going to be delta T. Now, the operational definition for a time interval is going to be T final minus T initial. So we use instants in time in our operational definition of an interval of time, time interval. Okay, so I can zoom out here. These are the ideas we need to do the lab today. We need to know what we mean by position, that is our distance away from the origin. And we need to know what we mean by time. Oh, change in position. I forgot something. Sorry. Position is a quantity that we call a vector. And that is, a vector is something that has not only an amount, but it has a direction as well. Now, what direction is this buggy car from the origin? Well, it's to the right of the origin. And this one, this final position, is to the right of the origin. Now, what if I went over here? See, 1, 2, 3. What if I told you, okay, the buggy car is 3 meters away from the origin? Well, do you see that there are 2 places that are 3 meters from the origin? Right? I mean, I could put the buggy car over here. That's 3 meters away from the origin. How do we distinguish between this location in space, this position from the origin, and this position from the origin? Well, what did you do on a number line in math class? You put a negative there. Now, what does that negative mean? I'm going to draw the vector arrow for this. It means, what's the difference between this buggy car and this buggy? They're both 3 meters away, but this one is to the right of the origin, so we'll make to the right of the origin positive. These are positive positions over here, and these will be negative. So I could say, x equals negative 3 meters. So what does this negative mean in this context? The negative means a direction to the left, to the left, to the left. Okay. So if you see positive 3, that means to the right. Okay? So when we're dealing with positive and negatives in kinematics, the positive will usually mean to the right, and negative will mean to the left. Or later on, we're going to do things up and down. Usually we say up is positive and down is negative. And we don't have to do it that way. I can make down positive and up negative as long as I know what I'm doing and define it ahead of time. I'm good. So this is called a vector quantity. A vector is something that has magnitude, that is, and that's the 3 meters is the magnitude, and then it has direction, and the negative sign represents the direction, and negative here means to the left. So 3 meters to the left, that's a vector. There are things that are not vectors. Okay, temperature. Okay, the temperature in this room is 70, what is the temperature in this room? About 75 degrees? 77 degrees. Okay, so the temperature of the room is 77 degrees to the left. Does that make any sense? I hope not. No, it doesn't. Okay, so if you give a quantity that it doesn't make any sense to put a spatial direction with, it's not a vector. It's called a scalar. A scalar is a quantity that only has magnitude. It doesn't have a direction, a spatial direction associated with it. Okay? And time has no spatial direction. I look at my watch, it says, okay, it's 10:47. You would never say, oh, 10:47 west. Like if I'm looking to the west, it's 10. No, that's stupid. Okay, so don't do that. Now, now let's also, last thing. What do I mean by quantity? What do I mean by a quantity? Let me put this up here. Quantity. You don't have to put it up there, just put it somewhere in your notes. Quantity. Well, a quantity is a measurable aspect of the universe. Okay? A measurable aspect of the universe. For example, my height is measurable. That is, I can compare my height to some standard unit of height or length. Turns out with my shoes on, I'm almost exactly 2 meters tall. That's very exciting. I'm the 2 meter man. Okay? However, there are things, so that's a measurable quantity. Your mass is a measurable quantity. How much time goes by is a measurable quantity. All these are things that I can compare to some standard length or duration, time or something. Temperature. Now, there are things, though, that are real in the universe that are not measurable. We can't compare them to some standard unit. Okay, for example, raise your hand proudly if you've ever been in love. Okay, how many of you have been in love? All right. Oh, very good, very good. Much better. Second period, nobody raised their hands. It's a very sad group. Okay? Okay. Hey, I'm proud to say I know what it's like to be in love. Okay? And still am going strong. Our anniversary's next week. But, right on, 26 years. But, let me just say this, though. It's not quite as ridiculous as it was at the beginning, right? But anyway, when you're in love for the first time, right? I mean, or when you're in love, somebody new, and you're just like, oh, well, that happened to me, 29 years ago, 28 years ago. When I met my wife, we went out. We were just in love, okay? And I have to tell you the story. I had an A going into my final exam in advanced thermodynamics at Cal Poly, okay? I was really good at thermodynamics. And we started dating like a week before the final exam. And that was a big mistake, okay? Because I had to study for this final, and I would sit up in the library and I would just look out the window and just like, oh, the world is so good. I'm so happy. I'm in love. I'm not going to, I don't care. I'm in love, So I ended up getting a B in the class, and it's all my wife's fault. Okay, I blamed her for that B ever since. So I don't think really love is something real. I mean, you experience it, but I don't think there's a standard unit of love that we can measure how much love you have. It's not measurable. Now, if you go to a carnival or something, they have those or an arcade kind of situation. They've got like these love meters. Have you ever seen the love meter? You put your hand on something and the light, you put your quarter in, and then the light goes up and tells you how much love you have or how much in love you are, right? Okay, it's total nonsense. Okay, here's what it is. It's a measure of how sweaty your hands are. If your hands are really sweaty, it's salt water kind of on your hands, and that conducts electricity really well. So your hands conduct electricity really, really fast, so the light goes way up, because they figure if your hands are really sweaty, you must be in love, right? Well, do this, get your hands all hot and sweaty, you're in love. Okay, then go wash your hands in cold soapy water and dry them thoroughly. Then put your hands on there, and you're not in love anymore, according to this instrument. So it's a great measure of skin sweatiness. It's not a good measure of love. Now, having said that, though, they do brain scans now. They've got these machines that can do brain scans. And here's what they have found. This is very interesting. People who are mentally ill have a certain kind of brain scan where certain areas of the brain are active and certain areas are not active compared to a mentally healthy person. And what they have found is that when somebody is in love, like in that infatuation stage, their brain scan is indistinguishable from somebody who is literally insane. Okay? So you literally are in crazy love. Okay? They call it that infatuation stage, and it lasts about 6 months. So if you're in a relationship and you're in that 6 month period, and you go, you can do it. I've seen some of you out there, by the way, So, but then 6 months go by and you just say, the magic just isn't there anymore, We're just not in love anymore. Okay, no, just calm down, okay? It's just your brain going back to normal. You need to come back to normal at some point. Doesn't mean you're not in love anymore. It just means you're not insanely in love anymore, which is probably a healthy thing. So don't make any rash decisions in the first 6 months of any relationship, okay? You may be making the biggest mistake in your life. If you still love the person after the infatuation stage goes, maybe they're the one, okay? But maybe before you get married, you should have to have a brain scan, and make sure that your brain is back to normal before you're allowed to make these decisions. I don't know. The ACLU may have a problem with that, but I think it's still a good idea. But anyway, things like love and truth, justice, mercy, certain ideas of philosophy and theology, these are all things that are very real. But they're not really scientific because we can't measure them. And science mainly deals with things that are observable and quantifiable. And so that's what we're going to be doing today, is we're going to be having fun with these little buggy cars, but even though they may elicit an emotional response from us, we're really going to be studying their motion and understanding their motion. So let's get to the lab.